So what I would like to talk about is a new variety of function. Up to this point, we had, in Math 72, or what they usually call Algebra 1, we had linear functions. Here in Algebra 2, we had radical functions, rational functions, and quadratic functions. And here at the end of the course, I would like to preview for you the concept of an exponential function, which is used to represent something like, the spread of a virus, for example. Now, not only is this a timely topic, but exponential functions are the topic of much investigation in Math 107 and Math 141. So whether you're planning to take Math and Society or Pre-Calculus 1, I hope that this will help you out a bit, this discussion. All right. So in this first video, what I would like to do is I would like to do some analysis, first of all, of a linear function. Now, the generic form for a linear function is mx plus what I'm calling a. I know that you may be used to mx plus b, but there is a reason that I want to use a different letter this time for the added quantity in the back. So I would like to call this form number times x plus number, mx plus a. We're given a specific example on the side. F of x equals 3x plus 2. So I'm just going to note that in this specific example, m is being replaced with 3, and a is being replaced with 2. Now let's make a table of values. Now if I plug in something like x equals, let's say 1 to this equation, what is the corresponding value of f of x, the output? Well, let me do some work on the side. This is where I'll put all my scratch work. 3 times 1 plus 2 is 3 plus 2 is 5. So 5 is the output that goes with x equals 1. What if I put in x equals 0? If I put in x equals 0, 3 times 0 plus 2, 0 plus 2 is just 2. So I'll mark that in the table as well. And let's just do one more calculation. Let's do x equals negative 1. 3 times negative 1 plus 2, that's negative 3 plus 2. That's minus 1. Okay, now I have a challenge for you. I want you to look real hard at this table. Where are you seeing the value of a, of this number in the back? And this one's a little bit harder. Where are you seeing this value of m? Where does 3 show up in this table? Now the value of a equals 2, can actually be seen in this table directly. It shows up right here. A is the number that is associated with x equals 0. So let me note that a is the y-intercept. It's the output that you get when x is 0. Put another way, a is the initial amount. This is especially appropriate if x represents time. If no time has passed and x is 0, then the output associated with that is a. Now here's the one that's slightly harder to find in my opinion. Where does 3 show up in this table? Well, notice this. Every time we move down one square in this table, every time we increase x by 1 unit, the outputs increase by exactly 3 units. Negative 1 plus 3 is 2. 2 plus 3 is 5. 3. So 3 is called the slope. is the slope of this line. And it's the amount that is added to y whenever x is increased by 1 unit. By 1. M is the amount added to y whenever x is increased by 1 unit. So A is telling you what the value was in the beginning, initially, when no time has passed. And M is telling you how the y values are changing over time. It's initially 2, and then with every additional x, the y value has 3 added in. All right, I would like to compare that with a new variety of function called exponential. And I've given you a specific example of an exponential function, 3 times 2 to the power x. Actually, I think I would like to alter this a bit. I would like to do 2 times 3 to the power x. This is a specific example of an exponential function which has the general form number in front times some other number being raised to the power x, not mx plus b or mx plus a, but a times b to the power x. So let's just do some initial calculations and build up a table of values here for this particular example. What if I plugged in x equals 1 to this function? What would be the result? Let's again do some work on the side. If I plug in x equals 1 and put 1 in x's position, then let me follow PEMDAS here. 3 to the exponent of 1 is 3. 2 times 3 is 6. So x equals 1 is paired with an output of y equals 6. Now let me try, for example, x equals 2. X equals 2. If I have 2 times 3 to the second power, then that's 2 times 9, which is 18. 18 here. Let's make it a little more interesting. What if I plugged in x equals 0? X equals 0. Let's go back and plug in x equals 0 to this function. 2 times 3 to the power 0. Take a moment. What happens when you raise a number to the power 0? The result of raising a number to the power 0, the result of that is always 1. So this quantity is 2 times 1. The result is 2. 3 to the power 0 is 1. And finally, I would like to do 2 times 3 to the power minus 1. Do you remember what happens when you raise 3 to the power negative 1? Negative exponents cause quantities to become reciprocated. So 3 to the negative 1 is the same thing as 1 over 3. So if I plug in x equals negative 1, the result is 2 over 3. And this comes just from using PEMDAS and just from using the exponent rules. Now here's the question. Once again, I'd like you to pause and try and look in this table. Where is the value of A showing up? Here A is 2. And where is the value of B showing up? B for base B is 3. Now that you've had a chance, I think that probably A, once again, is the easiest to find. The A value is, once again, the y-intercept. A is the y-intercept, or the initial amount. It's the y value that you get when x is 0. But this time, where does B show up? Where are you seeing a 3 in this problem? Well, notice this time, unlike before, when x is increased by 1 unit, when we move 1 space down this table, something consistent is happening to the outputs, but this time we're not adding a consistent amount. 2 to 6, I would have to add 4. 6 to 18, I would have to add 12. We're not adding a consistent amount, but this time we are multiplying by a consistent amount. Every time we move 1 space down this table, 2 times 3 is 6. 6 times 3 is 18. And that is the impact of the base B here. B is the amount that is being not added to y, but being multiplied to y whenever x increases by 1. So a linear function, whenever you increase x by 1, the slope is added to that. For an exponential function, whenever x is increased by 1, the base is multiplied to what you had before.